What is the product rule for radicals, and how is it used to simplify radicals? The product rule for radicals says that the nth root of a product AB equals the product of the nth root of A times the nth root of B. For example, the square root of 8 is equal to the square root of 4 times 2, and using the product rule, that equals the square root of 4 times the square root of 2. The square root of 4 simplifies to 2, and the square root of 2 is already a simplified factor. The square root of 12 can be written as the square root of 4 times 3. The product rule says that's the square root of 4 times the square root of 3, which equals 2 times the square root of 3. Similarly, the square root of 24 is the square root of 4 times 6. Using the product rule, we get the square root of 4 times the square root of 6, or 2 square roots of 6. We can summarize a general process for simplifying radicals using the product rule. First, write the radicand as a useful product. This may require some additional explanation shortly. Second, use the product rule to write the expression as a product of radicals. Next, simplify the radicals. And finally, repeat these steps as needed. That is, until no factor of the radicand contains a power that is a multiple of the index. Let's apply these processes to some examples. Instructions on these problems will be to simplify each radical expression. The square root of 20 equals the square root of 4 times 5. Using the product rule, we get the square root of 4 times the square root of 5. Now 4 times 5 is a useful factorization of 20 because 4 is 2 squared, and the square root of 2 squared simplifies to 2. To simplify the cube root of 24, a useful factorization of 24 is 8 times 3, because the cube root of 8 is the cube root of 2 cubed, and that simplifies to 2 with an additional factor of the cube root of 3. To simplify a fifth root, we'll want to factor out fifth powers. So the fifth root of 64 is the fifth root of 32 times 2, which, according to the product rule, is the fifth root of 32 times the fifth root of 2. 32 is 2 to the fifth, so we get 2 times the fifth root of 2. In general, to choose a useful factorization, we want to factor out the largest perfect powers for the index. If the index is 2, we want to factor out perfect squares. If the index is 3, factor out perfect cubes, etc. Sometimes we might choose to prime factor the radicand to look for the perfect powers to simplify. We've already seen this first example, but let's rework by prime factoring. The square root of 20 is the square root of 2 squared times 5. Using the product rule, that's the square root of 2 squared times the square root of 5, or 2 square roots of 5. Considering the cube root of 48, we want to write 48 as 2 to the 4th times 3. Since the index is 3, we want to split off or factor out perfect powers of 3. We can regroup using the associative law, then use the product rule for radicals, and finally simplify to 2 cube roots of 6. Finally, to simplify the fourth root of 162, we prime factor 162 as 2 times 3 to the 4th. use the product rule for radicals, and simplify to 3 times the 4th root of 2. Now let's look at several more complicated examples with variables to increase our comfort in simplifying radicals. We also want to watch out for when we need absolute value in simplifying even indexed radicals. To simplify the square root of x to the 7th, we first factor out all even powers and write x to the 7th as x to the 6th times x. Then use the product rule for radicals. To simplify the square root of x to the 6th, we can think of x to the 6th over 2 power using rational exponents. But we need to think about absolute value because x to the 6th will be non-negative regardless of the sign of x. On second thought, if we notice that an odd power of x is under an even indexed radical in the original problem, we can conclude in this example that x must have been non-negative all along. So sometimes there's a reason why we know that variables have to be greater than or equal to 0, even if we're not explicitly told that that's an assumption to make. To simplify the cube root, we want to factor out perfect cubes. Also note that we won't have to worry about absolute value with odd indexed radicals. We write x to the 23rd as x to the 21st times x squared. Use the product rule. We can use the definition of rational exponents to write the cube root of x to the 21st as x to the 21 over 3 power. Thus we get x to the 7th times the cube root of x squared. To simplify a 4th root, we want to factor out powers that are multiples of 4. Since 4 is even, we do need to be careful about the sign of the radicand. Since 28 is already a multiple of 4, we can use the definition of rational exponents. Or we can write 28 as 7 times 4. Either way, to simplify, we get absolute value of x to the 7th, and we need to keep the absolute value in this particular problem. Let's consider 3 final examples with multiple variables. To simplify square roots, we want to factor out even powers or perfect squares. Then use the product rule for radicals. Notice that y must have been greater than or equal to 0 to have an odd power under an even indexed radical, so the square root of y makes sense. X to the 4th and y to the 8th even powers are always going to be positive, so we don't need the absolute value in our final answer. This is another example of a square root with odd powers in the radicand. Thus, we can safely assume that x and y are both non-negative. Again, we want to factor out even powers. We'll write 80 as 16 times 5, x to the 5th as x to the 4th times x, and y to the 9th as y to the 8th times y. Then apply the product rule to the perfect squares and to the remaining factors. Simplifying the square root of perfect squares, We normally get absolute value, but in this case, we've already decided that our variables are positive. For our last example, let's consider a cube root. This time, we want to factor out powers that are perfect cubes or multiples of 3. We'll write 54 as 27 times 2, x to the 15th as x to the 15th, already a multiple of 3, and y to the 25th as y to the 24th times y. Then we'll use the product rule to split off the perfect cubes and the remaining factors under cube root signs. Finally, we simplify the cube root of perfect cubes, and we have odd index, so we don't have to worry about the absolute value issue.